Okay, welcome back. Hope that you're all doing well, taking care of yourself, and all that kind of stuff. What we're going to do today is we are going to start in on the next section in the text, which is on exponential models. And so what we're going to do is we're going to use some of the use the exponential equations that we learned about last week to model actual real-world data. And this is actually very interesting to be doing right now because the reason we're in this situation in the first place is because um, the coronavirus that is got us all running scared and staying home is growing exponentially. So at some point, maybe tomorrow, after we've done a few basic ones, we'll talk a little bit about how this all relates to the current mess that we all find ourselves in. Anyway, but for today, what we're going to do is we're going to focus on money, money, money. So we're going to talk about a compound interest formula, and then we're going to talk about a continuously compounded interest formula, and then that will lead us into a discussion of the natural base number, which is referred to as the number E. Okay, this will be a pretty easy day today. So here's the main thing that you need to know about compound interest and how it relates to um, exponential equations, not that, is this stuff right here. So here's the general form of the equation. This value right here is going to be the amount of money that we start with in our account, and we talked about that last week as being the A value or the y-intercept. So that's how many, creatures or whatever you're starting with in your population, and then what you're multiplying by each time to figure out how much this is growing by is 1. Again, this is 1 because that represents the original amount, plus the interest rate. But sometimes interest is added to an account more than once a year. And so if that's the case, then you need to divide the interest rate by the number of times per year that it's being deposited into your account. But then you need to multiply the number of years by, whoops, I don't want that. Multiply the number of years by the number of times the interest is being deposited. So here's what this all means. P is the amount that you're starting with. R is the interest rate. Don't forget to change that to a decimal. N is the number of times you're adding interest every year. T is the number of years, and then A is how much money you end up with in the end. So let's do an example of that. In this case, we are doing a population of a town, okay? So the population of the town started at 8,000, so I'm going to go 8,000 times 1. It says the population is increasing, so that means I'm going to go plus 2.5% as a decimal. I have to move the decimal 2 places to the left, so that's 0.025. In this case, I could divide this by 1 because it's increasing at that rate per year. But there's no reason to divide by 1, so I'm going to leave that. It's just 0.025. And then I'm going to raise that to the t power for the number of years. Okay? So then it wants us to rewrite this to find out how much the population is growing per month. Well, in order to do that, so this is the population equation per year. So in order to change this into a monthly growth rate, what I need to do is I need to take the annual growth rate, so that's 1.025, and I need to raise that to the 1/12th power because there are 12 months in a year. So So if I jump over to decimals on my fin and go 1.025, and I raise that to the 1/12th power, then that tells me from that I get 1.002059. So that means that our monthly growth rate is, if I take this and move the decimal over 2 places, would be about point, I don't know, I guess we can just go with all the decimals here, 2059% per month. So if we do that per month, then we'll end up with a 2.5% growth rate over the course of the entire year. Okay, so this question here, we can work through this one together because that was a little bit wacky. It says the population is growing annually 1.8%. I guess I don't need to do anything really with this, so I need to just go 1 plus 1.8 as a percent as a decimal is 0.018. And then raise that to, this time I want the quarterly rate, so I need to raise that to the 1/4 power to find my quarterly rate, and that's going to be pretty small because it's a pretty small one to start with, but 1.018 to the 1/4 works out to be 1.0044699. So that would, if I move the decimal over 2 places here, that would be about 0.44699%. Okay. All right. So that was fun. All right, so let's get into the good stuff. Let's make some money. So it says, Tamira invests $5,000 in an account that pays 4% annual interest. How much will there be in the account after 3 years if the interest is compounded? Annually, semi-annually, quarterly, or monthly? All right, so annually first, that's the easy one. So I'm going to go 5,000 times 1 plus, and I'm doing plus because I'm adding interest to my account. 4% as a decimal is 0.04. Technically, I'm dividing this by 1 because it's annual interest, but again, that doesn't affect it at all, dividing by 1, so I'm going to leave that out. And then I'm raising this to the 3rd power to represent the 3 years that I'm keeping the money in my account. So if I do that on my calculator, 5,000 times 1.04 to the 3rd power, Tamira will have $5,624.32. Okay? All right, let's see how that changes now if instead of putting interest in the account at the end of every year, we put interest in the account semi-annually. So that would be at the end of every other year. I think there's a way that I can do fractions on this. Just inserting no, not really. Ooh, look, that's fun. Oh, maybe this. No? No? Oh, on-screen keyboard. Oh, that's not helpful. This is all just garbage. All right, so I'm going to have to go... I have to go 0.04 divided by, we're doing semi-annually, so I'm going to go divided by 2, because semi-annually means twice a year. And then I'm going to raise this to the 3rd power, but since I'm putting interest in there twice a year, I'm not just going to put interest in there 3 times, I'm going to end up putting interest in there 6 times twice a year for 3 years. So let's see how much she has now. So original 5,000 times 1 plus 0.04 divided by 2. And I'm going to raise this basically to the 6th power. Now she's got $5,630.81. So you can see that in this case she'll have slightly more money than she did when we did it annually, and that is going to be always the case. The more often you put interest in your account, the more money you are going to end up with. So let's take that to the next level. Let's go quarterly. So that's 4 times a year. So 4 times a year for a total of 3 years would be 12 times total. So I'm going to change this to a 12, and I'm going to change this to a 4, and now I have slightly even more money, $5,634.13. And so let's do the very last one. Let's go monthly. So 0.04 divided by 12, because there's 12 months in a year, to the 3 because it's 3 years, but times 12 because we'll end up putting interest in the account 36 times in this case. So I'm going to go and change the 12 to a 36, and I'm going to change the 4 to a 12, and now Tamira ends up with $5,636.36. So again, you can see as we put interest in the account more and more times, more and more often I should say, you end up with slightly more money in each case. Alright, so here's one for you to try on your own to see if you are understanding what I'm talking about. $3,000, 3% annual interest, and we're going to compound it monthly. What's the value of the account after 10 years, and what's the value of the account after 100? Pause the video and give it a go. Okay, so let's see how you did there. So for the first one, I'm going to take 3,000, and then I'm going to go 1 plus 0.03. I'm compounding this, monthly. So I'm going to divide by 12. And then I want to do this 10 years, so 10 times 12 is how many compounding times we're going to have. So on the calculator, 3,000 times 1 plus 0.03 divided by 12. And then this is going to end up being to the 120th power. So we end up with $4,048.06 if we do it for 10 years. How about if we do it for 100 years? Because apparently now we're leaving money to our grandkids or some crazy thing. So we're still starting with $3,000. We still have an interest rate of 3% that is being evenly divided over 12 intervals. But now we're going to do it 100 times 12. So I'm thinking we're going to end up with more money there. Let's see, that's 100 times 12 is 1,200. So yeah, now after 100 years you would have $60,031.45. So if only you could find a way to do that, you could turn $3,000 into $60,000. Okay, so now we're going to talk about what happens if we continue to have more and more compounding periods. In other words, instead of just doing monthly, what if we did, 100 times a year, 1,000 times a year, 10,000 times a year, and so forth. And what you're going to see is, well, let's just do it. So I'm going to take this equation right here, because we're just going to keep it simple, and we're going to say, let's just say we put $1 into an account. And so here's the 1 that we're putting in. Here's the 1 that stands for our original amount of money. This is the number of times we're doing it per year. And then this is the number of times total. So let's see what happens as this, as we mess around with this. So let's go 1 plus 1 divided by 1, because this is just annually, to the first power. And if we do that, well, we get 1 plus 1 is 2 to the first is 2. So we would have $2 at the end of the year, and that makes sense because they're saying 100% annual interest, so basically they're doubling your money, okay? All right, now let's say we do this 10 times a year. So now I'm going to go 1 plus 1 divided by now 10, and then I'm going to do this to the 10th power. And if I do that, 1 plus 1 divided by 10 to the 10th power works out to be 2.5937. So you can see that we have compounded quite a few more times per year, and so now our amount of money has gone up. Okay, let's play again. This time let's go 100 times per year. So 1 divided by 100 to the 100th power. Just have to change a couple numbers here. And if I do that, I end up with 2.70481. Okay, so again, slightly more money, because we're putting interest in more times, so we're going to get more money. All right, let's keep going. Now let's put interest in 1,000 times a year. So this is to the 1,000th power, and as you would expect, I got a sneeze coming. We get a little bit more money, but you can see that the increase in the amount of money that we have is starting to level off. So in the very beginning we went up from 2 to 259, then we went up from 259 to 270, now we're only at 271. So things are still going up, but they're not going up by nearly as much. So now let's go 1 plus 1 divided by, what does that say, 10,000? 1, 2, 3, 4 to the 1, 2, 3, 4 power. And you can make a guess if you want. See what you think that's going to end up being. So I'll put in a couple more zeros, and then I get 2.718146. So now we're still going up, but only just a little bit, 2.716 to 2.718. So you can see that we are starting to level off a little bit. So if you think about how this would look on a graph, what's happening is as the x values are getting larger, we're starting to see what we like to call in the biz a horizontal asymptote. And it turns out that that asymptote, let me just do this last one, has a very important significant value. This one comes out to be 2.71826. So 2.7181, 2.7182, so still going up, but not by much. Anyway, so you can see those are getting closer and closer to a particular value, which is what we call the natural base, or E. And it is an irrational number. Decimal goes on forever and ever and ever, just like pi. But what that allows us to do is it allows us to come up with the formula for what's called continuously compounded interest, which doesn't really make any sense in a practical way, because it means that someone is constantly putting interest into your account, which of course you can't physically do, but by using this math formula you can figure out how much you would have if you were able to do that. And this is sometimes called the Pert Formula because it's P equals E times R to the T. Times E to the RT. And so anytime you see this word right here, continuously, you got to think this formula here, okay? So if you are being asked to compound interest monthly, or you're being asked to compound interest quarterly, semi-annually, annually, you're using this formula right here. But as soon as you see this word continuously, then all bets are off and we shift to this guy right there, okay? And this number E is actually a number on your calculator. On Desmos, you just have to go to the keyboard and type the letter E, and it will give you that. If we were in class and had one of my little calculators, you could see that there's an E button on those calculators. You might have to go second and then the LN button to get to it, but it's on there. So before we do a problem with compound interest, being compounded continuously, let's just ask this question. If we went back to this table here, we were doing, and we did 1 million instead of 100,000, would the answer, would the amount in the account increase or decrease? And hopefully that's a very easy question for you. We could say that it would increase. And that is because more interest means more money. So the more often you're depositing interest into your account, the more money you're going to end up having in your account. All right, so let's wrap this up with a continuously compounded interest problem, and then I'll give you some problems for you to work on if you want to try this out. And then I'll make another video of me going through those problems. It's a super fun new world we live in. Okay, so for this one it says Regina invests $12,600 in an account that earns 3.2% annual interest compounded continuously. So there's that key word that we're looking for. What is the value of the account after 12 years? And let's not mess with pennies, let's just focus on the dollars. So 12,600 is our principal, and then that's going to be times E to the, I need to change the 3.2% into a decimal. Don't forget to do that, or you're going to get a ginormous answer, which is sadly incorrect. And then we want to do this for 12 years. So if I type that into the calculator, 12,600. Like I said, you can just go to the keyboard and type in E. And then I want to do this to the, I got to throw some parentheses around this because both of the numbers are being raised, or E is being raised to the power of both of those numbers. So I should throw some parentheses around the 0.032 and the 12 so that we don't get confused. You would end up with $18,499, which is not so bad. Alright, so let me go back and change this here. You really, like I said, would be better off, if you put parentheses at the beginning and parentheses at the end of that. Okay? Alright, so one of those that you can try on your own. Pause the video if you would like and do that. Okay, pretty simple as long as you understand the formula. It's 125,000 times E to the 4.75% as a decimal is 0.04475. And then we're doing this for 15 years, and I've already broken my rule. This should all be in parentheses. Okay, so if you type that onto your calculator, 1, 2, 5, whoops, that's a 6, 1, 2, 5, 1, 2, 3, E to the parentheses 0.04475. 475 times 15. We're going to end up with, ooh, that's a lot of money, $254,885. So you have more than doubled your money. Nice job. And then if we waited 30 years, that would be exactly the same, except that now I'm going to change the 15 to a 30. So it's still 0.0475 times 30. And again, if we, it's easy to change on Desmo. And then we end up with, wowza, $519,000, or $519,732. So that's a lot of simoleons. Okay, so here's a handful of problems that you can work on your own if you would like to check your understanding of the material that we've gone over today. So I'm going to post this to YouTube and then take a little break, and then I will post a video of me going through these answers. So see you in a little bit.